come to section 3 of unit 1, and the section objectives are: 1. State and prove the commutative laws on union and intersection of sets. 2. State and prove the associative laws on union and intersection of sets. 3. State and prove the distributive laws on union and intersection of sets. And 4. Illustrate the laws in 1, 2, and 3 for any given sets. We will now consider commutativity properties. And the first theorem to be considered under commutativity properties is the commutativity of union. Let A and B be two sets. Then A union B is equal to B union A. So that is the property, commutativity property of unions. Let's look at how to prove this property. Now, suppose X belongs to A union B. What it then means is that X is a member of A or X is a member of B. Now, let's say X is a member of A. Then what it means is that X will surely be a member of A union B. Again, if we assume that X is a member of B, then of course X should be a member of B union A. Therefore, every element that can be found in A union B can also be found in B union A. Hence, we conclude that A union B is equal to B union A. Let's look at an example to illustrate the property we have just discussed. Let set A be X such that X is a whole number between 4 and 8, and set B be made up of X such that X is an even natural number less than 10. Then, if we list the members, set A will be 5, 6, and 7, and set B will be 2, 4, 6, and 8. Let's find A union B. To find A union B, we bring the members of set A, and we bring the union symbol, and we bring the members of set B. Then we put these two members together into a new set, and then we will have 2, 4, 5, 6, 7, and 8. And so we'll call this one equation 1. Now let's do the other way round, where we do B union A. So this time we'll bring the set B first, then we bring the union symbol, and then we bring the set A. And then we combine the members of these two sets to have 2, 4, 5, 6, 7, and 8. We will call this one also equation 2. Then we are going to observe the two answers, the answer in equation 1 and the answer in equation 2. And when you observe these two answers, you realize that they are the same. So we conclude that A union B is equal to 2, 4, 5, 6, 7, 8, and that is the same as B union A. Get two sets of your own choice and verify this property and discuss the answer with your colleagues. Still on the commutativity properties, this time we want to look at commutativity of intersections. Let A and B be two sets. Then A intersection B is equal to B intersection A. Let's prove this law also. Suppose X is a member of A intersection B. What it means is that X is a member of A and at the same time X is a member of B. Now, if X is a member of A and X is a member of B, it means therefore that X can be a member of B intersection A. Therefore, every element that can be found in A intersection B should also be found in B intersection A. We therefore conclude that A intersection B is equal to B intersection A. We will look at an example under commutativity of intersection, and we are going to consider the same sets that we considered when we were doing intersection of union. And so set A is X such that X is a whole number between 4 and 8. B, X such that X is an even natural number less than 10. By way of listing these members, set A is 5, 6, and 7, and set B is 2, 4, 6, and 8. Now we will find A intersection B, and so we bring the set A, we bring the intersection symbol, and we bring the set B, and we realize that the element that is common to both A and B is 6. So we call that one equation 1. We come round to do B intersection A, and so this time we bring the set B first, then we bring the intersection symbol, and then we bring the set A. Again, the element that is common to both B and A is 6. We call this one equation 2. We now look critically at the two equations, equation 1 and equation 2, and we discovered that the two are giving us the same answer. And so we conclude that A intersection B is equal to 6, and that is also equal to B intersection A. Therefore, A intersection B is equal to B intersection A. We now move away from the commutative property to associative property. And under this, the first theorem that we will look at is associativity of unions. Let's consider the three sets A, B, and C. Then A union bracket opens B union C bracket closed is equal to bracket opens A union B bracket closed union C. We will want to prove this property. We will start by saying that X is a member of A union bracket opens B union C bracket closed. This implies that X is a member of A or X is a member of B, or X is a member of C. If we suppose that X is a member of A or X is a member of B, then we can say that X is a member of B union C. If we again suppose that X is a member of A union B or X is a member of C, then we can say that X is a member of bracket opens A union B bracket closed union C. This means that every element that can be found in A union bracket open B union C bracket closed can also be found in bracket opens A union B bracket closed union C. We can therefore conclude that A union bracket open B union C bracket closed is equal to bracket opens A union B bracket closed union C. Let's consider example 3, which is on the associative property of union. Let's consider the three sets. Set A, which is A, N, T. Set B, which is T, A, P. And set C, which is S, A, P. So we will first do B union C, which gives us P, A, S, T. Then we are going to do A union into bracket B union C. So the answer we got when we did B union C, we'll find the union of that answer and A, and that gives us N, P, A, S, T. So we call that one equation 1. Now we first found the union of B and C. Now we are going to first find the union of A and B. So A union B will give us P, A, N, T. And then we are going to find the union of this answer and C. So the union of the answer we have and C will give us N, P, A, S, T. And then we call this one equation 2. Now when you study equation 1 and equation 2, you will discover that the two answers are the same. So that leads us to conclude that A union into bracket B union C is equal to N, P, A, S, T, which is also equal to into bracket A union B and then union C. We will move on to another property. The distributive property was the first one. Then it was followed with the associative property. So the associativity of intersection is left for you to do as an exercise. So we will continue to do the next property, which is the distributive property. And so we are going to look at distributivity of unions across intersections. And so we consider the three sets A, B, and C. Then the property says that if you have A union bracket open B intersection C bracket closed. It is equal to bracket open, A union B bracket closed, intersection, another bracket opens, A union C bracket closed. That is what the distributive property of union is saying. Distributive property of union over intersection. Now let's look at the proof. How do we prove this? We start by letting X be a member of A union bracket open B intersection C bracket closed. And so we are saying that if X is a member of the set we have mentioned, then it means that X can be found in A or X can be found in B intersection C. Let's now suppose that X is found in A. It means therefore that X can be found in A union B, and that the same X can be found in A union C. And so we can say that X is a member of bracket open A union B bracket closed intersection bracket open A union C bracket closed. Suppose again that X is a member of B intersection C. Then X can be found in B and X can be found in C. So the concluding part of this proof is in the next slide. From the previous slide, we saw that if we suppose that X is a member of B intersection C, then X is a member of set B and X is a member of set C. This implies that X is a member of A union B and X is a member of A union C. And so we can conclude that X is a member of bracket open A union B bracket closed intersection A bracket opens A union C bracket closed. Thus, every element of A union bracket opens B intersection C bracket closed can be found in bracket opens A union B bracket closed intersection bracket opens A union C bracket closed. We therefore conclude that A union B bracket opens B intersection C bracket closed is equal to bracket opens A union B bracket closed intersection bracket opens A union C bracket closed. Now, we will look at an example to illustrate this. So we will consider the three sets. A, which is made up of A, N, T. Then set B, which is made up of T, A, P. And set C, which is made up of S, A, P. The first thing we will do is to find B intersection C. B intersection C. And so we bring the set for B and we bring the set for C, and we find the intersection to be A and P. Then the next thing we will do is to find A union the answer we have. This will be shown in the next slide. From the previous slide, we got the answer for B intersection C, which is A, P. We are going to find the union of A and that answer. And so the union of A and the answer we got, which is the answer for B intersection C, will give us P, A, N, and T. We call that one equation 1. What we will do next is to find A union B and find A union C and do the intersection of the two answers and see if it will be equal to equation 1. So A union B gives us P, A, N, and T. And A union C gives us P, A, N, T, and S. We will now find the intersection of these two answers. A union B intersection A union C. So A union B we know is P, A, N, T. Then we bring the symbol for the intersection. And A union C we know is P, A, N, T, S. So when we find the intersection of these two, we get P, A, N, T. We call this one equation 2. Then we observe equation 1 and equation 2, and we discover that the two answers are the same. And so we can conclude that A union into bracket B intersection C is equal to bracket open A union B bracket closed intersection bracket opens A union C bracket closed. You can on your own try the distributive property of intersection distributed over union.